All right, today we're going to peel back the steel walls of a power plant and look at some of the incredible, kind of hidden science that keeps our lights on. It's a story about immense pressure, crazy heat, and a surprisingly elegant physics problem that has to be solved perfectly every single second of the day.
Okay, let's just dive right in with a question. It sounds simple, but the answer is anything but. Imagine this giant steel drum, right? It's filled with water that's being boiled into super high pressure steam. How in the world do you know exactly how much water is in there? I mean, you can't just pop the lid and stick a ruler in it. And getting the answer right is absolutely critical.
And this is why. This slide shows you the razor's edge that engineers have to walk. If the water level gets too low, you get what's called a dryout. The metal tubes get exposed to this blistering heat with no water to cool them, and they can literally burst. But if the level gets too high, you get carryover. That's where water droplets get blasted into the steam, and they act like tiny little bullets that just shred the blades of a steam turbine. Either way, it's a catastrophic failure. So, with the stakes being that high, how do you get a perfect measurement inside all that chaos? You can't see in there, so you have to use invisible clues. And the absolute best clue, it turns out, is pressure. It all starts with this fundamental principle: hydrostatic pressure. The idea is actually pretty simple. A taller column of water weighs more, so it pushes down harder, it exerts more pressure at the bottom. The formula here, P equals rho GH, just tells us that pressure is directly tied to the height of the water. So if we can measure that pressure accurately, we should be able to figure out the height. That's our starting point. Now, to use that principle, engineers came up with this really clever setup called a wet leg system. Basically, a device measures the pressure difference between 2 points on the boiler. The bottom point feels the weight of all the water inside the drum. The top point, though, is connected to this thing called a wet leg. It's just a pipe that's always kept full of cool, stable water. So this wet leg gives us a perfectly constant reference pressure. The instrument then just compares the two, and the difference should tell you the water level. Sounds simple enough, right? Well, it seems like the perfect solution. But there is a huge, hidden problem that can throw this whole elegant system way off, making the measurement dangerously wrong. And here's the villain of our story: density. The thing is, the density of water isn't some fixed number. As the boiler heats up and the pressure builds, the water inside actually expands and becomes less dense. And the steam above it, its density changes too. So the water in that wet leg on the outside, it stays cool and dense, but everything inside the boiler is a moving target. So let's go back to our main formula. If that little P symbol for density is constantly shifting, our entire calculation just falls apart. The exact same pressure reading could mean you have a high level of low-density water or a low level of high-density water. Without knowing the exact density at any given moment, that pressure reading is basically useless and potentially deadly. So how do you fix this? How do you account for a variable you can't even measure inside a sealed inferno? Well, the solution isn't some complicated piece of new hardware. It's an incredibly elegant insight that comes from the laws of thermodynamics. And here it is. This is the big aha moment. A boiler drum is what's known as a saturated system. Now, that's a fancy term for a very special state where water and steam are in perfect balance with each other. And in this specific condition, a kind of magic happens. Pressure and temperature are no longer independent. If you know the pressure, you automatically know the temperature. And you also automatically know the exact density of both the water and the steam. This is the breakthrough. This is the whole game. What seemed like this super complex problem with all these shifting variables, pressure, temperature, water density, steam density, it suddenly becomes a simple, single variable problem. All you need to know is the pressure, and that one number unlocks everything else. This table just lays out that relationship perfectly. You can see how everything is tied together, right? As the drum pressure goes up, the temperature goes up in a totally predictable way. And as that happens, the water becomes less dense, while the steam actually gets more dense. These aren't guesses. These values are all listed out in reference books called steam tables. They're all dancing to the same tune, and pressure is the conductor leading the orchestra. And that's why measuring pressure isn't just a convenient choice. It's the absolute best choice. Why? Well, for one, pressure is uniform. It's the same everywhere inside that drum. Temperature can have weird hot spots and cold spots, but pressure is consistent. That makes a single pressure reading incredibly reliable, and it makes the whole control system much, much simpler. Okay, so this is how it all comes together in the final calculation. You've got a computer that is constantly taking that raw pressure measurement,
At the exact same instant, it's also looking at the boiler's overall pressure to look up the correct current densities for both the steam and the water from those steam tables. It then plugs all of those live, correct values back into the formula to get a true density-compensated water level. It's this continuous, self-correcting calculation, all powered by one simple pressure measurement. Ultimately, that's what this entire engineering marvel is really all about. In this chaotic world full of variables that are always changing, the solution was to find that one single variable, pressure, that because it's in a saturated system, tells you the whole story. It is a beautiful, beautiful example of applying fundamental physics to solve a really high-stakes, real-world problem. You know, this elegant dance of pressure, temperature, and density is happening right now in power plants all over the world, just silently and invisibly keeping things safe and efficient. And it really makes you wonder, what other hidden scientific principles are quietly at work out there, forming the invisible backbone of our entire modern